Get going, testing, 1, 2, 3. All right. We should get going. All right, let's go ahead and get started with the word of prayer. Glad that you're all here. And day 4, I believe. Got some exciting things to talk about today. Let's go ahead and get started with the word of prayer. Father God in heaven, thank you once again for a new day. Thank you for blessings that we have just by waking up, breathing the air that you've made, drinking the water that you've made, and walking upon the ground that you have crafted with your own hands, with your intelligence, Lord. We thank you. As we discuss some tremendous things today, help us to understand in more detail the blessing that you have put inside of us and you've put around us to protect us and to keep us safe for all eternity. So we thank you, Lord. Once again, be with us now, we ask in Jesus' name. Amen. All right. Today we're going to talk about living in the fire. I've also called this glowing bananas. We're going to talk about radioactivity today, and we'll try to go at a good pace. I want to thank my wife for helping out and cleaning up afterwards for me, and she's wonderful, and we thought we had lost the remote to this, but we found it. Thank you very much. I can't make it without her, and in many ways. So today we want to talk about radioactivity, and before we get started, I actually have quite a few videos today. And because they do such a great job of explaining some key features along the way. So we're going to I have like 6 videos today, a couple minutes long. And I have just a few demos. And I wish I had more demonstrations, but dealing with radioactivity, well, you got to be careful with. So there's some issues there that you might understand. So I'm continuing to think about how to get some more demonstrations for this area. If you have some, let me know afterwards. So today is about radioactivity, our planet. This is a talk that I do for my class at Andrews University for general chemistry, parts of this. And it actually is some interactive part. I have questions. I wish we had some kind of clicker system like I had in my class to get some feedback from you. I know there's ways to do it online. I just haven't been able to have the time to get that figured out. But I'm going to show you some results, some questions from my class, and you'll see as we get along. From my general chemistry class. So we're going to talk about radioactivity, and I want to make sure this is distinguished and that we differentiate it from electromagnetic radiation that we were talking about yesterday. So there's some overlap between those two ideas, but in some ways they're different as well. So we're going to go ahead and roll the first video from a website called Veritasium, and they do a good job of explaining radioactivity here in a few minutes long video. So we're going to go ahead and roll the video on what is radioactivity.
At the end of the 1800s, physicists were staggered to find there was radiation coming out of all kinds of things, just dirt and rocks. The very first time this was discovered was with a jar of uranium salts that was left in a drawer overnight, and in the morning, a photographic plate that was next to it had been exposed, even though it had been in the dark all night. So where had the radiation came from? From this stuff, uranium salt it was. So to discover that dirt was giving out radiation, there was worse in store. They discovered that there were 3 different types of radiation going on. So they really had no idea what was happening. So what do as a scientist? You name it. So they named it A radiation, B radiation, C radiation. Well, that's a bit dull really, isn't it? So maybe let's go for something more sciencey. Alpha, beta, gamma. Yeah, that's much better. And I've got an example here. I've got some alpha, beta and gamma radiation, gamma sources here. I also have a Geiger counter, which is a little device that gives off a click when it detects radiation. So I can hold it over the source. You can hear you get a lot of clicks. So what are the different types? So our alpha, it turned out, pretty much completely blocked by paper, whereas the beta and the gamma makes basically no difference. So if we try lead, our alphas are completely blocked, strontium, the beta is pretty much blocked, but our gamma source, it makes basically no difference. So we can even go to a thick, solid piece of lead. And you can still see some things are getting through there. So we could try. There's a bit penetrating through. So, but I think I must be thicker than lead. So what are our three types of radiation? Scientists eventually worked out that the alpha radiation is matter, so it's 2 protons, 2 neutrons. That's the nucleus of helium. The beta source gives out electrons, and the gamma source gives out electromagnetic radiation.
The last one, the gamma radiation, was what we were talking about yesterday. That is electromagnetic radiation. That's very high energy. It can cause damage. In fact, all of these do. All these different types of radiation cause damage. As you can see, the alpha, I like to relate that for my students. The alpha particle and even the beta, they're particles. They're like golf balls. They're like baseballs. They're very, very tiny, but they're particles. And so we like to think about which ones cause more damage. Is it the alpha particles or is it the gamma radiation? Which one causes more damage to biological tissue? And it turns out that the alpha particles, the large ones, cause more damage. But they are easily stopped by something as thin as a piece of paper. And that's very important. Because if there is this type of radiation that's around us, let's say the alpha radiation that's coming from rocks or something as thin as dead skin will block alpha radiation. So it's believed that part of just our dead skin is there on top of us just to give us some protection from radiation. That's amazing. Now the beta, which is just electrons, and the gamma, that's dangerous light, those can go through like dead skin, but they kind of go through materials and they can cause some damage along the way, but they don't cause nearly the damage. So the problem becomes if you had some kind of alpha emitter and you ingested it and it's sitting inside you shooting off these helium particles, it can cause a lot of damage. And then we'll talk about that later. Now that guy must have known something. Why did he put it to his head? Why did he put radiation to his head? That was really crazy. Or was it? So we're going to learn more about that as we go along here. All right, so summary, particles, alpha particles, okay, they're helium atoms, beta particles, electrons, gamma radiation, I just think of it, it's a form of light, okay? And so you can't see it, and well, you can't see any of these things because they're too small, okay? And they are constantly coming off of material. Well, which materials? That's what we're going to think about here this morning as we think about particles. Now, there are a lot of elements on the periodic table that are radioactive, and I've highlighted them on my slides here on the periodic table. The ones in yellow are radioactive. They're usually really heavy, big elements from the periodic table. There are other what's called isotopes, forms of the different elements that are in white that have radioactive isotopes to them, but anything over around polonium, I think it's around 84, 85 on the periodic table in terms of the atomic number, they're radioactive. So there's quite a few elements that are radioactive. So that's important to know. Right? Where do we find them? Many of those elements are not naturally occurring, so that's great. But there are a lot of naturally occurring radioactive materials all around us. So that's good to know. And radioactivity actually solved one of the, or at least understanding it, solved one of the important pursuits that we'll call them scientists or alchemists had for many years, and that's being able to transmutate elements into gold, right? Because if you can turn lead into gold, oh man, then you can go sell it or use it for money. So people wanted to have gold. And actually, scientists have learned how to make gold other ways by new inventions and being able to sell those for lots of money. So we've been able to make gold in other ways. But it turns out radioactivity explains how elements like mercury that I'm showing here can undergo a process of that emitting of radioactivity, and it turns the element into another one. So mercury, liquid mercury, it would take maybe millions of years, but it will turn into gold if you have the right isotope of mercury. And it will, if it's the radioactive type, it can turn into gold, but don't wait around for it. Like I said, probably millions of years. So transmutation of the elements was occurring all along, and scientists really started to figure that out late 1800s, early 1900s, and so transmutation really does take place. And so that's pretty cool. So alchemy is real. Now, along with these particles that are being emitted, there's a few other aspects and qualities that I want us to be familiar with. And there is a great video about the understanding of the atom that the BBC has put together. And I show clips of it in class, and I'm going to show you a clip now that teaches us a little bit more about radioactivity and what scientists have done to use it, to understand it. And there'll be some important qualities and properties that we want to learn from this short clip on this BBC video about the atom. And so there's one other aspect that this video brought out about radioactivity that I would like us to draw attention to. So they talked about the particles coming off, and they didn't get into detail about the different types, but they added one aspect, I'm going to get my slide back to where we were here, to it, and that was the element of heat. These things were warm to the touch just in and of themselves. And that is an important property that we want to come back and think about a little bit later on. But the danger of radioactivity we also want to discuss too, because it is very dangerous, because it was burning the skin, x-rays, and we know these things can lead to some bad things for our health that we're going to talk about in just a little bit. But the heat aspect, we cannot forget. We want to come back to that. Now we're going to continue. I hope I put this video in there. Bullets that never run out. I'm pretty sure I got that one in there. And so if we have this video, we're gonna learn. It's a continuation of that previous clip here, and hopefully that video is in here. I think it is, and we're going to continue that experiment. Ernest Rutherford, with his graduate students, they were shooting these alpha particles through the gold, and for days and weeks, these graduate students would sit there and look for these little flashes of light, and they didn't see anything unusual. They said, hey, that's just going right through. We don't see anything. And Ernest Rutherford said, all right, let's move the detector and move it on the other side, close to the radiation source. And they eventually found that some of these alpha particles bounced off. And they deduced from that there was a dense nucleus to each atom, and that when these alpha particles hit that dense center, they would bounce off. And they were able to determine not only that there was a dense center, but it was positively charged, and it was, they could roughly determine the size of the nucleus of an atom relative to its size, about 1/10,000th of the size. Amazing experiment, great way to understand the atom. But the thing is that I want us to get from that is that radioactivity just doesn't seem to stop. And we've learned that that a lot of elements that are radioactive, they can just be emitting radiation for some of them for seconds, some of them for minutes, some for days, and some for thousands and millions and billions of years, that some of these particles will just keep coming out. Why is that? Why would we have such dangerous materials that are constantly emitting this radiation? And so we need to learn some more things about this radioactivity, and thanks to a wonderful woman scientist, Marie Curie. I think she was actually born in Poland, but did most of her work in France. And you can see her life there from 1876 to 1934. She actually coined a lot of the terms radioactivity and some of the descriptive properties of radioactivity. It was part of her PhD dissertation. And she loved this stuff. It was glowing. She would carry it around in her pockets and play with it in her hands. And it is to the point where, like, her cookbook and her chairs and everything that she touched are radioactive. And you can go in with Geiger counters and still see all these things. And just amazing. So she didn't know about it. It just was cool. It was glowing for a lot of this. She did end up dying not too young. I think you can calculate her age there. I think she was in her 50s, late 50s when she died. But she did die of complications from the radiation and how it affected her blood. And I just like to share a story about Marie Curie, and I like to inspire our students and our young ladies to get into science. And her hard work really helped us to understand this whole field. Her PhD advisor, Henry Becquerel, gave her a big task. He said, I'm going to give you a ton of this rock that we think is radioactive. We know it has this element uranium that they had discovered that was in it. He says, but I think there's something else in there. And they were going to use these photographic plates to detect the radiation coming off. So he gave this task to Marie and her husband Pierre, and he said, I think there's some new elements in there. And so this 1 ton of pitchblende came from the Ore Mountains in Central Europe. So it's not necessarily everywhere. There's certain rocks that have more than other. A ton is about what you would put in the back of a pickup. And so for 2 years, her and her husband did a lot of chemical processing to try to find these special elements in there. And after this ton of rock, they were able to get a few grains, just a couple of parts of a gram, 0.1 grams. It's hard to even show you, but it's a few like grains of salt. And she discovered 2 new elements. One of them was, well, they didn't have a name for it, so she coined it polonium after her home country of Poland. And it was 300 times more active, more radioactive than uranium. And then she found another element, which they called radium, and it was 1,000,000 times more radioactive than uranium. So Henry Becquerel was correct that there was other elements in there, and there was actually 2 of them. And so Marie Curie gets credit for discovering those 2 elements and their properties, and she was able to get her PhD. And so she ended up winning 2 Nobel Prizes for her work. I think it was one in chemistry and one in physics. And so just amazing. Science is not for men. Science is for everybody. And I just want to share, even from my class, it's nice to see. Actually, it's over the years that I've been at Andrews, we tend to have more young ladies in our class than we do young men, and maybe 60-40. And so there's actually, the balance is tipping the other way, that we're having more young women going into science, at least I'm seeing in biology and chemistry, and that's great. And that hopefully we'll get a balance in terms of faculty and scientists working out in industry between men and women, and I think that time is coming, and it's already happening. So we need everybody to be working on these problems. It's not just guys need to be in science. All right, so one of the neat things about being able to detect this type of radiation is a Geiger counter. And I actually have one right here, just got it, and it's measuring the background radiation of this building right now. And the way that it works is this radiation enters inside, it can get through the glass tube, so this really only measures alpha and beta, and beta and gamma particles. As they go inside a tube, they cause the gas inside this little tube to ionize, it charges it, and it can make a click sound. And so I have a little bit, so I have this here, and it's measuring the background. I don't know if we can get the cameras to zoom into this Geiger counter here. You can find them on Amazon. This was probably about $100. And I have it measuring the background, and it's a very small number. I'm going to read you the number right now. It's around 12 counts per minute. And that's really low, but there is radiation that is happening right now all around us. From the building materials, from you, from me, things are just, they have radioactivity in them. And I can hear it clicking. I don't know. So I actually brought something that was radioactive. And we're going to see if we can use this microphone, and it's kind of clicking away here. And I have a gamma emitter that I'm going to put right up next to it. Can you guys hear that? Okay, and I can take it away. And this could be kind of fun because you can carry it around and see if there's things that are radioactive. And I was going to bring my phone up here, but you can put, I can shine a laser on it, and that doesn't do anything. And you can just try to bring all sorts of objects next to it, batteries and phones, and these things are not radioactive. Okay, only special materials that we find in the ground and isolate them are radioactive. Okay, that's cesium right there. And the tube is behind it. And if I just get even close there. So I'm thankful to our physics department. They had some of these samples I was able to bring. Now, they have, we've noticed some stoneware. I think it was some Fiesta ware. It has some natural radioactivity in there, if anyone's aware of that. So our physics department back in Andrews has some of that. and we were testing it, and it was pretty radioactive. So now I can go and test these things. I've taken it in different parts of my house to see if there's radioactivity, and there's always just a little bit. There's always just a little bit going on, and it's just kind of flying around. So, okay, the counts are pretty high right now just because I put the cesium radioactive material next to it. Now, you may be saying, oh man, he's going to get radioactivity because I put it next to my hip here, the sample. But it's okay, because we're going to teach you some more things along the way, and it's going to be okay. It's going to be okay. So we're going to ask you some questions, and you can raise your hands here. If you like, did anybody have an x-ray performed on you before? Okay. Yeah, I've broken a few bones. Sorry, Mom and Dad. They were accidents. So yeah, a lot of you have had x-rays. Now, what are some of the risks that you may encounter if you have too many x-rays? So I like to give my students some choices. I said A, maybe your skin will fall off if you have too many. B, your bones will glow. C, an increased risk of cancer. D, you'll genetically mutate into a superhero. E, your pocketbook implodes. And what do you guys think is the real risk of getting too many x-rays? C. Oh, you guys are great. All right, and I always get a few votes for D. And if there were more adults, I'm sure they'd pick E, your pocketbook implodes. But yeah, no, it's an increased risk of cancer. And we're going to describe more about that. But this is the danger of being around too much radioactivity. You're going to say, oh no, I'm going to get cancer of the hip or something by putting it in here. No, just wait. This is an amazing story. So an increased exposure to x-rays and other radioactivity will lead to cancer, and that is bad news, as we all know. And a lot of this was not known, of course, to Marie Curie and others, and it took special events in history here for this exposure leading to cancer to be known. And there's a very interesting story, so I'm just going to take a moment to tell it. That has to do with wristwatches. And back in around World War I, people were interested in wristwatches, and they loved them so much they would, of course, wear them around. But they wanted to tell time at night, and so they had the dials, right? They didn't have the digital ones, and so someone said, "Oh, why don't we use these radioactive materials? They glow. We can create a little paste that glows, and we can paint them on to the dial." And people can read their watches at night and be able to tell time at night. So so companies that said, hey, let's just take this radium and we'll paint it on to the watch face, and this will solve the problem. We can read that at night. And so these companies would hire young ladies who would take their paint brushes and dip it into the radium paint and paint on the little tick marks so they can know what time it was. Well, in order to make it look nice and to get a nice fine tip on your paintbrush, they would lick the paintbrush. Paint, lick, paint, lick, paint, lick, paint. And nobody knew the health consequences to this. And the cancer that can result from all that radiation exposure doesn't happen within a few minutes or with hours or days. It took years, and a lot of these young ladies would work there for a year or two and then leave. And it wasn't until a few decades later that I should read more of the story, but they kind of got back together, and in various ways. I think some of them had cancer, and they thought, man, I think it had something to do with where we were working with the radium. And as these young ladies got together and they realized they were all having cancer of the mouth and the tongues and teeth and throats, and it was sure enough, it was licking that radium that they traced back and can connect that in a legal case. And they figured out that these young ladies, as they were, licking this radium paint, were actually being exposed to dangerous levels of radiation. And it wasn't just that they were around it, but they were ingesting it, and so getting it around their mouth. They had painful, disfiguring conditions, and some died from that radiation. So not good. And the Radium Girls, I think they might even made a play or something about it, and a theatrical production, and bad news. And so it's things like that we've learned over the years that sure enough, radiation exposure will lead to cancer. It starts to break down your DNA. Your DNA and your cells do not function properly, and that leads to mutations, and then your certain cells will start over multiplying, creating cancer. So too much radiation is bad news. And if we start to think about it, why is there a world that has radiation in it. That seems like a very dangerous and a bad thing to have. Did God intend and design that we would have cancer in this world? And I don't think we even agree that that would be a possibility. So why is it even here? So X-rays, gamma rays, all of these different types of particles emit these radiation, this radioactivity. In fact, it's often called ionizing radiation because it really transforms your material, a lot of organic materials, into ions, and that's the problem. So I'd be curious, where do we get the most exposure to radiation? Is it from this medical imaging? Nuclear power plants, nuclear blast, radiation from the sun and the earth itself. Maybe we'll do a quick poll. We'll just do it by hand. I'll just how many people think it's medical imaging? How many say power plants? How about fallout from the nuclear blast? We've got a couple. And radiation from the space and sun. Okay, lots of hands there. And the earth itself. Okay, I'm seeing some good hands, and I think I see some knowledgeable people out there. All right. So we're going to talk a little bit about the bombs, the atomic bombs that have resulted and have been tested over the years. And so you can get an idea, just to help you understand what's been happening with the nuclear technology over the years. So this little graph, it's actually a fun little poster, and it's talking about brute force. So in this picture that you can see on the screen, that it's describing the brute force here of atomic bombs. And of course, there was a race to make bigger and better bombs mainly between Russia and the United States. And we've been able to, just create bombs that are much more powerful than the ones that were dropped in Japan. And so over the years, there's some great videos. You guys should go watch them. I probably should show them. I had fun watching them again last night. But the United States and Russia would go back and forth building the biggest one. And eventually, Russia built one that was, it was like 30,000 times bigger than the one that was dropped on Japan, the ones that were dropped in Japan. It was called Tsar Bomba. And 50 megatons. They had to drop it from a plane. I think it was over the North Sea or north of Russia. And the bomb actually had a parachute on it, so it would drop slow enough so the pilots could get away. And there is some video footage of that. And if you can't read the little phrase on there, it says, "For when you have to absolutely, positively annihilate everything." And it's what's called a demotivator poster instead of a motivational one. And I find that scary. And just the technology that we have that has been developed on nuclear blast and these bombs, just amazing and incredible and scary all at the same time. And so I would be curious to know, what do you guys think? How many nuclear explosions have there been since 1945, those first ones that were dropped? Has there been about 10, 50, 200, 2,000, or 10,000? And how many people think there's maybe been around 10? Okay, 50? 200. There's been at least 200. Yeah, get some good hands there. 2,000? A few more hands. 10,000? Yeah, maybe a couple hands. I think I have what my students voted. Yep, this is what my students voted a couple years ago. And you can see a distribution. When I see this, when my students click in, they don't know, right? That means people are guessing. And that's typically the case. So we're going to roll another video in just a second here. A Japanese gentleman put together a video of each one of the detonations. These are the tests. These are the ones that have been dropped since 1945. And it's a stunning little visualization, a map of the world, and it shows which country and which and where on the global map these bombs have been detonated. And of course, we know only a couple have been with people, so they're out in the middle of the ocean or on islands and remote locations. So amazing video. So let's go ahead and roll the next video. after seeing that, I asked this question again. Actually, I asked it many times throughout the class or a couple of classes. And I think I do have what my, so the answer is actually the Earth itself. And after that, my students actually would say the fallout from nuclear blast. Because after seeing that, I'm like, oh, I want to change my answer. I had no idea there was over 2,000 detonations. And it was in the early 60s that those really large ones were being perfected. But it turns out, after all of that, even knowing that we've dropped so many bombs, 2,000 of them, or detonated them, it turns out the Earth itself is way more radioactive. We get the most exposure from the Earth itself. And how is that? Well, a lot of it is just there's certain elements that are radioactive. Potassium has a radioactive isotope that just travels around with regular old potassium. And so we tried to find it in bananas, and it's just hardly enough there to be detected. But in blocks and in certain types of materials, you'll find it. You'll find that radon, that's often just coming out of the ground, can get trapped in basements, and that can lead to a lot of radioactivity exposure that humans get exposed to. So we'll continue to talk about radioactivity on this planet, and the Veritasium YouTube channel has another amazing video about the radioactive places on Earth, and one of the guys on that channel takes around a Geiger counter to some of the most radioactive places on Earth. So let's go ahead and roll that video and learn about the radioactivity on our planet. This was not supposed to be an anti-smoking campaign, but I don't know what their beliefs are, but that sounds pretty bad. And it certainly is. And so you could go on to multiple websites and try to see what your radiation exposure is. And certainly we see one of the roles of our air is actually blocking us from other types of radiation besides the different parts of the electromagnetic spectrum. So we're thankful for the air. Those particles are helping us. But the radiation exposure that mainly humans are being exposed to here on Earth, probably the biggest is from radon. And as scientists are looking at it, this looks like it could be one of the biggest contributors to lung cancer as we're breathing it. It's a gas, and it's heavy. You can't see it. It's colorless, odorless, and you don't know it unless you have a special detector. That's why when houses are being sold, you often have to get a radon test. But from this graph, it's hard to read. But so I consider radon to be radiation that we get exposed to from the Earth. The other parts, terrestrial, internal, everything adds up to the Earth being probably the most radioactive place that we're exposed to. The sun is a close second to that. And then the medical and x-rays and those kind of things, examinations come in there. Of course, if you're getting exposed, if you're having more of these techniques performed on you, you're going to get exposed to more of that radiation. So it's interesting, they have a little graphic in there, you can't read it. It says from fallout, it says less than 0.3%. So those 2,000 plus nuclear detonations are hardly a blip on the exposure that we get. Hardly a blip. And a nice quote from this website here from the Nuclear Regulatory Commission. Since the beginning of time, all living creatures have been and are still being exposed to radiation. Nonetheless, most people are not aware of all the natural and man-made sources of radiation in our environment. So what's going on here? There's a couple of theories that go on that even though we're getting exposed to this radiation, we're at the level that nothing happens to us, and that's probably true. Some people believe if you get any radiation exposure, it's bad news. But we're really in this background where no effect is observed. Why is that? Why is that? And why is there even radioactive materials on our planet? Why would anybody do that? And one of the answers to this problem is that they give off heat. Why is that important? Why would they give off heat be important? Carter, this is where we're going to need some help, and Christiana. So sorry I didn't have too many demos, but we're going to do one up here right now, and we'll hopefully not burn down the place. We're going to play with a little bit of fire up here. This is one of the fun things of being a chemist, and we're going to light some things on fire and show how we can protect ourselves from fire, but also test it out a little bit. So Carter, you're going to come on my left side over here, and Christiana, you can come up here and just stand for a second. All right, Carter is going to light something on fire. We've practiced this. And I have here some rubbing alcohol. It's kind of taken off the thing, and it says flammable. And so I'm going to put a little pure rubbing alcohol in here. So it's something I can get at work. And I'm just going to put a piece of paper and soak it in there. And get it nice and soaked. You're going to get ready with that in just a second. And I'm going to make sure I hold this not over that. Carter, you're going to light this, and you know what to do right afterwards. Okay? So we're going to light that. Nice fire. And we're going to put that in there. We'll let it burn for a second. Okay? Put that in there. Okay, we smother it so the oxygen can't get there, and it will go out. Does it still burn? All right, it's pretty much out. And it has pretty much disintegrated and burnt up. No surprise, that's kind of what we expected. All right, and this time, though, we're going to add something to the alcohol that's still in there. Christiana, why don't you go ahead and add a little bit of, what do you have in your hand there, young lady? Water, excellent. All right, and you're going to add some in there. Okay, keep going. Okay, good. All right, it's a little about half and half. I find that to be about the right amount of mixture. Good job. And yeah, we'll just make this just a wee bit smaller. Okay, we're going to soak this in here now and light it on fire. We're going to do the flame away from that and go ahead and light that on fire. Okay, it's going to burn for a second. We'll put that in there. Oh, I think it went out already. I had some water in there just to put it out. Okay, I don't know if you guys can see. We'll hold this down. Did that get burned up at all? No, actually didn't really get burned up at all. By adding in some water, the heat goes into the water and it doesn't burn up at all. Is anybody willing to try this on something a little bit more valuable? We got a dollar bill or something they can contribute? We can try to see if we can burn some money. Carter, you want to see if you can go fetch your allowance? I mean, not your allowance for the week, but contribution. No, we'll give it back. So far, I've had somebody give a $100 bill once, and that was kind of a rare one. What do we got? We got a dollar bill. All right, that'll be good. We'll give it back, at least whatever's left of it. And we'll see if we can burn something without burning it. Okay. All right, we'll get it all nice and soaked here in our special fluid of water and alcohol. And here we go. Are you ready? He is ready. And we'll light it. Okay, it's on fire. We'll put it down in there. Go and smother it just in case. And let's hold it up. And I don't know if I'll hold it up here. Okay, it was on fire and is now not burnt. Yay! All right, thanks you guys. You had at least one little demo. All right. So there was something protecting the dollar bill and the flame, and that was water. There was a protection that I knew I could have to build in there. All right, so we're going to keep that in mind as we think about the heat and the radiation that comes from. Well, it's important to know that the radiation that comes from these elements like uranium, thorium, potassium, they actually have, that radiation will continue to come off for billions of years. And it's not that we sit around and wait for a billion years, right? Nobody can do that, but we can measure the rate at which the radiation's coming off and how long it would last in the material. And what was surprising for me to note as I was doing research for this a few years ago, that much of the heat inside of the Earth is there because of this decay of the radioactive materials in the Earth. Somewhere between half and maybe as much as 90% of the heat inside of the Earth comes from the radioactive decay of elements. Well, why is that important? It's extremely important for a number of reasons. The heat that's in our planet, it's enough to help keep the right heat and viscosity for the mantle and the plates, so we have this plate tectonics. And a lot of scientists will tell you that life is here on this planet mainly because of plate tectonics. And it's able to help recycle the crust and a lot of materials in the Earth. And probably the second, or maybe even more important than is that the magnetic field of this Earth is a result of the heat inside of the Earth creating a molten core that creates, it's called the dynamo effect, and it's spinning and moving iron, and it creates the magnetic field. And we need to have a lot of heat in the interior of the Earth to create this dynamo effect. And without the heat, or if it was heated another way, the heat would go away and dissipate in a faster rate if it was using another type of heating source. And so the heat in the core of the Earth is for plate tectonics and magnetic field. And we talked about it yesterday how important the magnetic field is. So why would someone who's designing a planet use such a dangerous material as radioactive elements to heat a planet? Well, number one, it is a long-term heating solution to go along with the long-term heating solution that we call the sun. The sun is capable of producing energy for billions of years, and so are radioactive materials. So we have a nice match there for the heating of both above us and below us. And the other thing that's important to know about radioactive materials is that they can generate a lot of heat with a very small amount of mass. And to top it off, and I'm going to talk about that mass conversion here in just a second. And lastly, yes, there's radiation, that's bad news, but we're not giving off greenhouse gas. If you were heating it through combustion of some sort, you would be giving off carbon dioxide. You'd be messing around in a great way with the composition of our atmosphere. And it's been worked out that the amount of energy you can get from 1 pound of radioactive materials that have been processed or used for generating energy, 1 pound will give you the equivalent of 10 million pounds of coal. That's pretty amazing. So if we think about that for a second, you do not need to have a whole lot of mass to get a lot of heat and energy. That means you can keep a planet smaller. So you can get the right size, which will have the right gravity to hold on to everything. So radioactive elements become an awesome way of heating a planet, keeping the mass small enough, but having a lot of energy there to keep it at the right temperature in the inside. It's actually an awesome, beautiful design if we think about it and in the right detail. That right there alone is amazing. Okay, so we see some design there that if we had too little radioactivity, it would be too cold, and plate tectonics and the magnetic field would not work well. If we have too much, we know the problem would be life would be seriously destroyed, and the chances of getting cancer would greatly increase, and life just could not exist if we had too much. So I see chemical design right there. But how do we live in this heat? How are we able to live in such a dangerous place with all of this heat coming off? Is there something there protecting us? And the answer is yes. Just like we just did the demonstration, having some water in there helps us. But what helps our bodies? Well, we need to understand when there's a mistake that's happening, how do you correct it? Can you identify the mistake that's taking place in this little quizzy thing, this cute little test here on the screen? Raise your hand when you're able to find the mistake. Okay, some hands are going up. And so we can get a few more hands. Can you find the mistake? How many people have seen this before? Okay, probably almost the same hands that have gone up already. See, when you know what the mistake is, it's easy to find and adjust for it. Well, I'm going to, in the interest of time, I'm going to tell you what the mistake is in this little thing. I'll just say it because a lot of you can't be heard. The mistake is there are two thes. It says, can you find the mistake? See, it's easy to see when you know. You guys are looking at the numbers, because that's what I did the first time. I'm like, okay, is it the rainbow colors? They're missing a number. It's forgetting a zero. No, there's two thes in there. Our brain went right over it. All right. When you know what the mistake is, it's easy to correct for it. So we know that cancer, a lot of it is caused by radioactivity, and that leads to DNA damage. We need to go and talk about DNA. Is there anything that is out there to help our DNA from keeping damage? And so this is a picture of the double helix, and it's inside each cell, there's about 6 feet of DNA when you stretch it out. It's very thin, but when you stretch it out. So what happens to our DNA? Well, it turns out over the last 30 years, in our last video here, it has been discovered that, at least so far, there's 5 known mistakes that happen as DNA gets damaged, And it turns out there is a repair mechanism for each one of those 5 known damages that takes place. And there's a cute little video here that we're going to watch to describe the repair that is constantly taking place with our DNA.
The DNA in just one of your cells gets damaged tens of thousands of times per day. Multiply that by your body's 100 trillion or so cells, and you've got a quintillion DNA errors every day. And because DNA provides the blueprint for the proteins your cells need to function, damage causes serious problems, such as cancer. The errors come in different forms. Sometimes nucleotides, DNA's building blocks, get damaged. Other times nucleotides get matched up incorrectly, causing mutations. And nicks in one or both strands can interfere with DNA replication, or even cause sections of DNA to get mixed up. Fortunately, your cells have ways of fixing most of these problems, most of the time. These repair pathways all rely on specialized enzymes. Different ones respond to different types of damage. One common error is base mismatches. Each nucleotide contains a base, and during DNA replication, the enzyme DNA polymerase is supposed to bring in the right partner to pair with every base on each template strand, adenine with thymine and guanine with cytosine. But about once every 100,000 additions, it makes a mistake. The enzyme catches most of these right away and cuts off a few nucleotides and replaces them with the correct ones. And just in case it missed a few, a second set of proteins comes behind it to check. If they find a mismatch, they cut out the incorrect nucleotide and replace it. This is called mismatch repair. Together, these two systems reduce the number of base mismatch errors to about 1 in 1 billion. But DNA can get damaged after replication too. Lots of different molecules can cause chemical changes to nucleotides. Some of these come from environmental exposure, like certain compounds in tobacco smoke. But others are molecules that are found in cells naturally, like hydrogen peroxide. Certain chemical changes are so common that they have specific enzymes assigned to reverse the damage. But the cell also has more general repair pathways. If just one base is damaged, it can usually be fixed by a process called base excision repair. One enzyme snips out the damaged base, and other enzymes come in to trim around the site and replace the nucleotides. UV light can cause damage that's a little harder to fix. Sometimes it causes 2 adjacent nucleotides to stick together, distorting the DNA's double helix shape. Damage like this requires a more complex process called nucleotide excision repair. A team of proteins removes a long strand of 24 or so nucleotides and replaces them with fresh ones. Very high-frequency radiation, like gamma rays and X-rays, cause a different kind of damage. They can actually sever one or both strands of the DNA backbone. Double-strand breaks are the most dangerous. Even one can cause cell death. The 2 most common pathways for repairing double-strand breaks are called homologous recombination and non-homologous end joining. Homologous recombination uses an undamaged section of similar DNA as a template. Enzymes interlace the damaged and undamaged strands, get them to exchange sequences of nucleotides, and finally fill in the missing gaps to end up with 2 complete double-stranded segments. Non-homologous end joining, on the other hand, doesn't rely on a template. Instead, a series of proteins trims off a few nucleotides and then fuses the broken ends back together. This process isn't as accurate. It can cause genes to get mixed up or moved around, but it's useful when sister DNA isn't available. Of course, changes to DNA aren't always bad. Beneficial mutations can allow a species to evolve, but most of the time, we want DNA to stay the same. Defects in DNA repair are associated with premature aging and many kinds of cancer. So if you're looking for a fountain of youth, it's already operating in your cells, billions and billions of times a day.
even in the simplest organism, these DNA repair mechanisms are going on. Now, there's a lot we can comment about what they said in that video, especially at the end. We're not going to do a whole lot of that right now because we're running out of time. But it's amazing. There's damage, and there's the ability to fix it. So, and this damage is taking place all the time. So if you think if life is trying to get started and evolve, you'd say, oh, this must be great. You're getting all this genetic mutation that can help things evolve. Yeah, but if you're getting so genetically messed up as soon as you're getting started, you can't. You need the repair mechanisms in there. So without the repair mechanisms, life doesn't even have a chance of getting started on its own. And even the simplest creatures like bacteria have these repair mechanisms. In fact, that's where they've been studying it. And we know we have the same type of repair mechanisms. So there's this damage that's being taken place, but we can be assured that we have mechanisms inside of us repairing these breaks. The gentleman, and there's been multiple groups of scientists who've been working on it, were awarded the Nobel Prize in 2015 in chemistry for their study of these processes that are taking place. So that's amazing. Let's do one more little test here, see if you can find the mistake. Raise your hand if you're able to find the mistake in here. Okay. How many people have seen this one before? A few. Okay. I'm going to tell you because I've seen it, and we need to finish up our talk here today. And it's in the phrase that the little doggy, I guess, is saying, can you spot the mistake, right? So it's in the words again. You were looking at the numbers and the letters there. No. So it's in the words. So if you know where to look, you can find the mistakes. So if we think about it just for a second, how would a code or a book, if something damaged it, how would a book know to repair itself? How would a computer code or something know how to repair itself? How does DNA know how to repair itself? Well, how do these problems in chemistry that are chemical breaks and things that are happen, how do they know to get fixed? Well, if you know what the mistake is and what's going to happen, you can design a system to fix the mistake. And so I see design here again that, yes, we live on a radioactive planet, but the design is inside of us and all living creatures to protect against these mistakes that can happen. And obviously, as time has gone on, keeping up with those mistakes, I believe our bodies and creatures we're not getting better at doing that, it's beginning worse. So I start to see a lot of these same design issues here. Hey, we have the radioactivity, we need it to be a long-term heating solution for our planet, but we have the protection mechanisms against the damage that is happening. Amazing things that we're just learning here in the last few years and how this works. So I find this to be a very important topic, of course, because as the deeper we dig in the science, we see all these parts that need to be there at the same time. Otherwise, life cannot exist. And so I think we need a renewed look at a lot of these overlooked ideas. We just say, this is cool stuff. Thank you, science. And then we'll see these videos and hear these videos in there. Well, this just helps evolution to take place. Well, how do you get the right mutation rate for evolution to even occur? It has to occur at the right rate. If genetic changes are happening too fast, life dies off. It's too slow, then you don't get any changes. So even evolution, if it did exist, had to be designed to have the right rate. And so the chances of evolution taking place, the odds of that are getting lower and lower and lower. The deeper we look at these things, we see all of I see it like gears that are all fit in so nice. The radioactivity in our planet, the heat, the magnetic field, the lack of electric field, our air and all the components, and having the right amount of nitrogen, all of these things come together, and I see them as gears. I see a space vehicle going through the solar system. And if we're trying to build something to send astronauts out there, all these things we have to think about, and yet it's all here on this planet. And it's not something that we just commonly find on every planet. And the more we look, we're going to see we're going to continue to see more ways of it not working, I think, than in how it will work. And I believe, as it says in Jeremiah 29:13, that when we continue to seek God in our work that we're doing, that we will find God, especially when we're seeking Him with all our heart. Tomorrow I'm going to talk, it'll be my last talk, and I'm going to present 3 of the top challenges to evolutionary thinking, naturalism, and you may say, well, that all sounds pretty good. Now, what I've been talking about this week, that's my area. I like to talk about these are not things that are necessarily new, but maybe you haven't heard them. But I think these are the three greatest challenges to evolution. And I don't see any reasonable counteraction to these three main ideas that we're going to talk about tomorrow. So I call it well, well, well. And so I look forward to you guys coming back for the last talk, and we're gonna hopefully give you some more ideas to think about and how God designed this world. And it's just amazing. The deeper I look and we put all these pieces together, and I see a picture of God, the designer, in this planet. Let's end our time together with prayer. Father God in heaven, I thank you for making this planet, because you did make it. And it is amazing. And you made us. And you made us to live on this place. We have just the right amount of repair that's taking place inside of us to counteract some of the ill effects that are there that have happened over the years here and how you've designed this planet and what's here right now. So we thank you for that. Lord, if we can trust you with our lives now, I hope we can find the opportunity in our lives to trust you with every part of our life. That we would give you all of us, so that we would be in your hands, you would take care of us, and we know that you're there to take care of us for all eternity. So thank you for your blessings that we get to experience every moment. And so go with us now as we get to just go around and be in this amazing spaceship that's going through the space right now that we call Earth, our home. In Jesus' name I pray, amen. All right, God bless you. If you have any questions, you're welcome to come up here and talk while we clean up. Thank you for being here today.